Hi everyone, my name is Jasmine Liu. I'm a PhD student at the University of Chicago, and today I'll be talking about a research project called ProtoPCB, Reclaiming PCB e-waste as Prototyping Material. This work was done in collaboration with Rishitha Boddu and Pedro Lopes at the University of Chicago. In this work, we explore how building tools to allow the printed circuit boards that often become e-waste can be reclaimed by applying computer vision and computational search methods to find ways of prototyping new circuits on these existing PCBs, such that PCBs no longer need to be fixed designs, but can be used to prototype a ton of new systems. Before diving into our work, let me give you a brief primer on PCBs. When prototyping with electronics, you might employ a variety of strategies depending on your experience level and needs. But when it comes to where you build your circuit, there are four main approaches. First, breadboards, which operate by allowing you to insert component legs into sockets that are connected across rows and rails. Then, protoboards, which require you to insert component legs into plated holes and then solder those connections. Next, breakout boards, which are printed circuit boards designed to accommodate specific surface-mounted component footprints. And last, there are printed circuit boards, which are manufactured for specific circuit designs, often in PCB fabrication labs. This is the industry standard, as PCBs are found in all modern devices, so it's a necessary step in going from prototype to product. Now, the first three are probably the most common for early prototyping stages. If you go into any lab, you'll likely see shelves with a mixture of these. This is because these three types of boards are inherently reusable. You can anticipate using them for a bunch of different electronics projects. But using these boards severely limits the type of designs you can prototype and the type of components you can prototype with, which is why much of the electronics industry is using PCBs. There are a few reasons for this, but important to know about PCBs is that they are absolutely necessary when working with surface-mounted components, which make up the vast majority of electronic components. PCBs are also manufactured for a specific design, allowing for highly compact form factors and flexible for specific constraints. However, PCB's biggest strength is also its biggest weakness. As you can see, the PCB here was designed for a handheld game. It only does that, and that's why it's so compact. The same game on a breadboard is much clunkier. So the benefit of PCBs is that they're designed to enable SMD component use, but they're also designed to be single purpose. However, this process of prototyping with PCBs can be extremely time-consuming and wasteful. This is just a small portion of what we had in a class learning about designing PCBs that Pedro Lopes teaches at the University of Chicago. And what's more, these are not easy to make for the most part, and including for the class, people are sending these PCB design files to manufacturers, so it's a very involved process from design to manufacturing to shipping. Given that PCBs are so time-consuming and wasteful to work with, we take a different approach. Instead of manufacturing a new PCB for every prototype, we explore how to reuse already existing PCBs to prototype new circuits. Now, even a really talented electronics engineer would have a hard time identifying how to optimally reconstruct a circuit on a PCB meant for an entirely different purpose. But with ProtoPCB, we built a tool that computationally solves for how you can implement new circuits onto existing PCBs, making the process actually accessible. Let me demonstrate how our tool does this for this circuit. This user is about to use our tool to fit this new circuit design onto an existing e-waste circuit board. The user loads in their schematic and e-waste board files and hits run circuit match analysis. Once full circuit matches are found, ProtoPCB renders the best circuit match, showing the user where to solder their components, as well as where to make interventions like adding a trace or cutting a wire. So, how does the search process actually work? We're using computer vision to analyze two layers of the board. First, the copper, and then the masks. The copper shows how all parts of the PCB are connected, the underlying traces, and the mask shows where you can solder components to. First, we look at the mask layers to find places components can be soldered to. To find ways of physically fitting components onto a board, ProtoPCB searches using a mask of the component footprint and scanning across the layer for intersecting areas. Using this approach of intersecting geometries, we can widen possible matches beyond just one-to-one matches to also include matches within another footprint, as well as matches across different footprints. Using this approach, we can find different locations where components can be soldered onto the boards, regardless of whether or not those locations were originally designated for that specific component. In this window, we're matching a 555 timer that has a pin layout like this. The UI shows 16 ways you could position that component when soldering onto the board. For simpler and more common footprints like this resistor, the number dramatically increases. Now there are hundreds of places we can solder components to. So now that we know how we can solder components onto these boards, we then turn to leveraging the existing traces in a PCB to realize how to connect those components together until the reused PCB is able to realize a circuit it was never designed for. Using the trace layers, we can create a mapping of all those board connections, considering the traces and pads connected. With this information, we can then start our algorithmic search process. First, we identify a component to start with, usually one with the most pins, and look at a component placement match. Then we take a look at one of the nets touching the component and look at the relevant pin. We consider the pads and traces touched by that pin and try to find possible component matches for the other components in that net. We continue to repeat this process until the circuit is completed. So our greedy search process is going to do its best to find as many ways as possible to fit the new circuit onto this PCB. But sometimes it will be physically impossible to do so because of a missing connection. Well, here ProtoPCB will also identify ways to use interventions to implement a circuit, including adding a wire, cutting a trace, or using multiple boards. Pulling it all together, our GUI displays all the possible ways of implementing that new circuit onto an existing PCB, net by net. And you can see where to solder components, what underlying traces are used, and where to make interventions. In practice, how well would this work? Well, we took a look at 9 different boards of varying complexity and explored how often we could implement boards of lower complexity onto these other boards. On the left, we have a table showing when boards could be implemented on another board, either as a full match, where all the components could be soldered onto the boards, or a partial match, where 80% or 50 to 80% of the components could be fit. On the right, we show how for each circuit, what percentage of components could be fit onto other boards on average. And across these PCBs, an average of 81.7% of components could be refit onto another board. This was really exciting and showed how viable this approach of reclaiming PCB e-waste could be for building most types of circuits. To conclude, whereas originally one PCB was designed for one purpose, by applying a suite of computational methods, we can find a plethora of new ways to reuse these PCBs. So today I talked about how ProtoPCB offers a new prototyping strategy which allows harnessing a lot of the benefits of prototyping with PCBs, but by minimizing the waste inherent to that process. This new strategy was completely conceptualized by prioritizing reuse and examining how we could support it. From there, really interesting research questions emerged that forced us to rethink how PCBs are made and what limitations they had. By thinking within the constraints of waste and what we already have around us, a very different fabrication pipeline emerged. ProtoPCB is part of an ongoing thread of my work in my PhD about computational recycling, exploring how computational methods can inspire new tools and systems for better recycling e-waste. Alongside reusing PCBs, I've also explored a tool to assist reuse of components and how to think of recycling along the stack over the default bulk material recycling approach that is most common today. These works were heavily inspired by each other, and new ideas around reuse continue to pop up with every new method. So I encourage the broader HCI community to also consider how they might approach building tools for computational recycling. Thanks so much for listening to this talk. Feel free to email questions or come talk to me at the CHI conference.